Hello everyone. My name is Antoine Thomas. I'm a consultant in geosciences. I've been working in chemical EOR and polymer flooding for more than 10 years, and today I'll try to provide a fresh or at least a different look at what I believe is a never-ending comeback of this technique in an industry which is now chasing carbon efficiency. So the presentation will be divided into three parts. The first one is about polymer flooding itself. Why now? Why ever? What are the benefits? In the second part, I will try to discuss the challenges and the hurdles which have been slowing down implementation over the last decades. And in the last part, I will try to give some ideas to streamline the process. So basically, how we can move much faster from the concept in the lab to the field to get results. So a couple of slides for the introduction. So many countries today are looking for alternative sources of energy, trying to move away from fossils. It's like the tomorrow I quit. But the thing is, shifting away from fossils, which have been at the core and are at the core of our developed societies and developing societies, will take some time. It will likely not happen overnight. And at the same time, you need energy to fuel the transition. And oil production is declining, which means that because of less discoveries and lower budget, we will have a problem, which is how will we fuel the shift from fossils to other sources of energy, in addition to considering, of course, savings, sobriety, and optimization. So when you think about where to find the oil needed to buffer the transition, and to be a bit provocative, we can say, well, what about where we left it, which is basically in all the mature fields with very low recovery factors, very often below 40%. So that's why EOR makes a lot of sense. And as an engineer, well, I'm not very happy when I hear that basically you have a lot of oil left, like more than 60% is left in the fields, which this recovery efficiency is not bound by the laws of thermodynamics. I mean, it's a very low recovery factor. And among the easiest and most implemented technique to improve this recovery factor, you have polymer flooding, which is basically water, just more viscous. It's a very well-known concept, been discussed over more than 50 years. Many field projects, low risk, high return, which means that if it fails, you're injecting water, but if it does work, which is the case very often, then you get at least 10% OOIP, which is very good value. So, and again, we'll try to discuss why it's relevant now and how can we speed up implementation and what are the challenges remaining to make this happen. So all in one slide. So once again, polymer flooding is just viscous water. So all this concept of fractional flow, mobility ratio, and sweep efficiency have been discussed back in the 50s. I put a few names between brackets for people who might not know these authors, researchers. And so, I mean, the thing is, it's applicable basically where water flood is or can be implemented. Again, when you look at fractional flow, these are the basic fundamental mathematical equations behind this technique, which is if you improve the viscosity of water, you get more oil faster. So the question is, how do you increase viscosity of water? You can put ice cream or polymers, but if you have polymers, they will help to recover oil in reservoirs which are heterogeneous and or, this is important, where you have unfavorable mobility ratio. So even though you have, for example, a low oil viscosity, but you have large heterogeneities, then it makes sense to increase the viscosity of water. As for the envelope of application, now we have projects injecting in low permeability reservoirs, like in carbonate in Middle East, high temperature in the same places, but also very high salinity waters, sometimes even wondering if there is water left in this brine, given the amount of salt, like some projects in Russia or Kazakhstan. So now, why polymer flooding? I mean, why now? Why ever? Why should we even consider this technique? Well, imagine that you can improve your energy balance sheet, which is you use less energy to produce more energy, or you use less water to produce more oil. So this is the basic concept, and I will just give an example in the upcoming slides. why this technique is really critical in today's attempt to basically decrease carbon footprint while providing energy to fuel the transition. Also, because as stated by the IEA, the production is declining, but much faster than any plausible fall in global demand. So, if there is no investment into exploration, then we will have a problem. We start to see energy crunches, and it might probably get worse if we don't find a way to basically try to plateau this production. And also because the oil and gas industry is probably oil and gas, but a lot of water, like 3 barrels of water for 1 barrel of oil, which means, again, there is something here that should be fixed, or at least some efficiency to be gained for sure to minimize these volumes. So let's start with the savings, because that's probably what everyone is interested about, which is you inject less water, then you produce less water, and you spend less energy handling the water, which is the concept behind also polymer flooding. I could highly recommend reading the papers from Farsadeh, with reference it at the bottom of the slide, because they use the laws of thermodynamics and mathematics basically to look at the whole production cycle. And with this concept of exergy, which is basically how much energy is used to do some useful work, then they show that above 80% water cut, you lose a lot of exergy. For example, 100 kilograms of CO2 are produced per barrel above 96% water cut, which is huge. So when you consider now polymer, it means you increase the energy efficiency just because you decrease the volume of water used, handled, and the water cut. And despite the fact that exergy investment might be high and the cost high for chemical EOR compared to water flooding, this investment is many materials. And so in the end, the CO2 intensity of the oil produced from polymer flooding is much less compared to water injection at large water cuts. And also the CO2 basically is sequestered in the form of polymer because it's not getting oxidized or changing. So once it's in the reservoir, it's either produced, recycled, or disposed of, or basically stays there. So, of course, something which has not been considered in that study is the reuse of polymers that can really increase the savings. And when I say it, even if it's sometimes better not to have to, I mean that if you can reuse polymer, it means either you have injected more than one pore volume, or you have early breakthrough, which means it's not still very, very efficient, and there is a conformance problem to be fixed, really to, again, increase the efficiency and not waste too much energy. So what are the challenges for me to overcome? And I will start with a kind of acid joke, which is, what is for me the biggest problem with tertiary recovery? Well, I think it's the fact that it comes after secondary recovery in books, and that many people consider EOR as the end of the road. But for example, I mean, we know that water injection was cheap and easy in the past, and water is almost everywhere, so you can use to displace oil and maintain pressure. But now we know also that the efficiency of this technique is quite low. Again, 35% recovery factor is not much. So, I mean, what do we wait to change the approach? If it's not really efficient, why do we keep doing the same thing over and over again if we know that in the end we will have the same problem and we will have to fix it? Other thing is, of course, industry is risk adverse and loss adverse, which basically is no one wants to fail and or spend in vain. Of course, if you spend money, it doesn't work, then well, who's happy? No one. The thing is, with polymer flooding, we know how to make it work, and we know it's quite simple and straightforward. So again, I think it's a bad excuse now to consider this statement. Knowledge management, always the same problem, probably always will be the same problem, which is people change careers, companies, jobs, team changes, the skills disappear, reappear. Well, I think we have probably just to centralize the knowledge somewhere, kind of our chemical EOR books, and be sure that it's easily accessible to new generations and that the knowledge is really gathered in one place and not dispatched into many different papers and things like that. Last but not least, I think there are other fears, like people say we need water to understand injectivity and our reservoir. Say, okay, well, what's the difference between 1 and 2 to 3 centipoise water in understanding the reservoir? Probably not much. And of course, again, what is a good injectivity? Because if you only recover 35% of the oil and you are recycling and cycling water, basically you have an injectivity which is also based on a very low sweep efficiency. So, I mean, yeah, you have good injectivity, you have good rates, but you are not pushing anything anymore and you have very bad sweep. So maybe we can also revise the way we look at this concept. So how to move faster to the field? Few slides, again, a couple of ideas, not much time, but I'll try to start with something which is, well, first letting go of false hopes, which is what is the representativity between lab and the field? And when I ask this question, I mean honestly, because heterogeneity is underestimated in the way we approach and assess the reservoirs. And then when we pick a piece of that to evaluate through cores, which are too small, then polymer solutions and samples are different. The solution in the lab is pristine, no problem, no degradation, very nice water quality. And when you go to the field, it becomes much different. And the samples are the same because you use small pieces of samples from sometimes lab. It would be much better to use industrial batches, which really we have in the field, that will have some quality variation just because that's the way it works, even though they are small, depending on raw materials and manufacturing processes. So these are different too. Injectivity, which is probably the most important parameter to make a business case and to ensure that it's going to work, you cannot evaluate in a lab. So, I mean, it might be better to spend a bit more time in a small pilot than in the lab, just to be sure that we get the right parameter in our evaluation. And of course, the flow regimes are different because in the core, where it's fixed rate, linear flow, compared to well, where you have radial flow with perforations, fractures, or slotted liners, then it's very, very much different. So what's left? I think first, of course, R&D, which is viscous fingering, study of that, polymer interactions. Comparing polymer. I think for me, in the lab, you should compare polymers to find the best candidates. And of course, be very careful with the values you get for the best candidate. You can compare retention, resistance factors, resistance to degradation, and also their stability. So getting relative information, not precise. That's going to be say like it's true and this is what's going to happen in my reservoir, because it won't be the case. And something I got from a contact of mine last year, a bit provocative, but I found it funny, which is what we do in the lab is we gather data to build inexact models, to build the business case, to please the management, to get the funding, and to later quantify how wrong we were. So, well, a bit provocative, but someone said that all models are wrong and some are useful. So. Step 2 is see bigger. So very often we go from the lab to the pilot to the full field. I think it's very small proposition, nothing very fancy here, but I would propose to consider a pilot budget included in the lab studies. You can do both. And when I see people spending $500,000 in the lab over 5 to 10 years, with this amount of money, you could do much more in the field. For example, you can look at injectivity. You can do very small pilots for 1 or 2 months, even with a small spacing, to get other values such as pressure or recovery, even quantify some retention. You can design the field to avoid lab studies. For example, if you are afraid of degradation, you can have more perforations. If you're afraid of shear thickening, you can have more perforations. You can check the logistics. You can check real-life QC, because, again, if the water quality changes or if the polymer sample changes, you need to have something in place before you go to large deployments. And in the lab, you keep doing what you are doing, which is viscosity resistance factor, comparing polymers, filter ratio, retention, and now you have accelerated procedures for aging and even some universal curves for resistance factor and viscosity. And then instead of going to large fields, you go to phase deployment, which is basically using modular units. You start small investment, and then you move or you increase the number of modules basically to really keep this under control in terms of cost. And also, of course, very important is discuss industrial samples and logistics first, because if you find a good candidate in a lab, but when you try to go to the field and you need to build railroad tracks or new access roads and it's too expensive and you just stop everything here, well, I would recommend sometimes just to look at the big picture first to be sure that you don't forget anything. Step 3, all models are wrong. We discussed this a little bit, which is heterogeneity is underestimated, near reservoir effects are poorly constrained, and injectivity is not known a priori in the lab and or poorly modeled. So, and also I think it's very important to question the inputs in the models, which is a lot of people use viscosity curves instead of resistance factors, which is a big mistake because resistance factors, or I mean for the same viscosity curve, you will have different resistance factors depending on the polymer type, but also permeability. Do I understand my near wellbore? Which is probably the most important question, especially when you go to the model or modeling stage. Do I need some keywords? For example, do I need the shear thickening if I can basically design my well to avoid having this problem? And are my mathematics used in my model correct? I've seen recently a paper saying that the Peaceman model was not applicable to non-Newtonian fluids, which is basically what is used in a lot of softwares. And of course, quick comparison of scenarios, like for example, fixed pressure, variable rates, or fixed rate, variable pressure, where the truth lies in between, to be sure that you don't get strange answers from the model, which says basically you can't inject 3 centipoise. And if you get this answer, then you have to not ignore field data where a lot of people have been able to inject much more than that. Step 4, revisit all beliefs. So in 2018, the IEA was writing a couple of sentences. We'll go through them together, which is the life cycle cost of EOR can be competitive, but it entails upfront capital requirements and long payback periods. Long payback periods, I mean, yes and no. If you design the pilot correctly with a nice spacing or per volume injectable per year, it's fine. Regarding capital, again, if you start small with modular units, targeting sweet spots, sweet zones, and then you de-risk everything and you increase slowly or you move, then this goes away. Second is incentive to pursue EOR is often highest when and where there are concerns over resource scarcity. Well, I'll probably not comment this today because everything has changed since 2018. There is a preference in the upstream industry that can generate for projects that can generate fast return. Well, your project requires time to plan, test, and implement, and generates incremental production in the later year of the life fields. Again, if you move faster from the lab to the field, you build on existing experience, and you design a correct pilot, then that's not true anymore. You can get answers within a couple of weeks or months, getting already confirmation about the validity of your approach and your business case. EOR has become a niche business and skills and expertise are not widely available. This is what we're discussing, so there is a need here, of course, to keep the skills available and to gather knowledge somewhere for everyone to get access to fast. And the cost for EOR have been down since 2014, but the cost of all the projects, including shale and offshore developments, have come down more quickly. Yes, okay, maybe, but probably look at what's happening now in the shale and offshore industry and exploration business. The strategy and philosophies have changed very much. So what was true 3 years ago, 4 years ago, has changed dramatically. And last step is to use new tools. So for example, artificial intelligence could be used to analyze more data, refine models, analyze scenarios, and also match, predict, and adapt in real time. Once you get production data, you get breakthrough, you go back to the model, or the machine learning goes back in the model and analyzes different scenarios, explaining why this is happening. And then you can have a look and say, okay, it makes sense, doesn't make sense. Also on the right side, you have a lot of AI extracting more geological information from seismic. And now you can understand why, for example, some wells are producing, some aren't, and where to go for infill drilling, which zone to choose for a pilot, and these kind of things. So much less risk to have out of zone injection or problems. And also monitoring, because the thing is, if you don't know what's happening in the reservoir, then it's difficult, and you have to wait to see an answer or no answer in the producers or in the injectors. So just gave two examples of passive and active light monitoring solutions, which basically can help you target zones in the reservoir to update the model and the movements of the fronts to make sure that everything is going as per the plan, which I think is very valuable too. And in conclusion, I'd just like to say a sentence from Farstad again, which is that polymer injection into reservoirs with large water cuts can be a solution for two challenges: meet the global demand by increasing recovery and reduce the CO2 intensity of produced oil. The thing is, they discuss this for large water cuts, high water cuts, but we know that it's going to happen someday. So my last sentence would be that prevention is better than cure, and now we have everything we need to make it work efficiently and economically. So with this, thank you for listening, and I'll be happy to answer questions should there be any.